Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show CFD analysis of a wind tunnel which has got single entry and two exits, and this analysis will be done using ANSYS Fluent fault tolerant meshing. For starting fault tolerant meshing, we have to save this model as FM database. Let us save it. The model is saved with the extension of FMD. Next to that, we have to start Fluent launcher from here. Let us open Fluent fault tolerant meshing. Next to that, we have to import that CAD model. Let us import that file from here. We have got two models of wind tunnel. One is without baffle, another is with baffles. Let us import that model with baffles. That means at the junction of two exits, we are having some kind of baffles to divert the flow of fluid. Let us open this one. Let us create meshing objects. This is the model. We can see the location of the baffles. Let us have a segmented view from front plane. You see some baffles are provided at this location, right? So normally fluid will be passing from this entry and it will be diverted little bit of, and it will be going in the upward direction also and the downward direction also. So we're having two exits. This is exit 1 at the bottom side, and this is the exit 2, and this is the entry, and little bit of fluid is diverted with this baffle, right? Next to that, we have to describe what type of analysis it is. Definitely it is an internal analysis, so we need to check in internal fluid flow. With the default setting, we need to describe the geometry and flow. For initiation of CFD analysis, we need to have a closed volume. For that, we need to provide some caps at the inlet and exit locations, right? Let us put some caps at the entry location, and zone type will be definitely velocity inlet, and we can rename that cap as entry cap or inlet cap. Let us create that cap. It is made. Next to that, we have to create two separate caps for the exit openings. Let us select exit 1, that is the bottom cap of the exit opening, and zone type will be definitely pressure outlet, as this one is the exit, and we can rename this one as exit cap 1, or you can say exit 1 cap. Let us create that cap for the exit 1. You can see that cap is created here. Next to that, the final cap at the exit 2 location. Let us select that cap, and the name of this one should be exit 2 cap, and the zone type will be definitely pressure outlet. Let us create that cap. All the caps are created. You can view the inlet also. That means we have got a closed volume. Next to that, we have to identify the region. That means fluid domain should be identified. In this case, we need to provide two domains. One will be fluid domain, another will be void domain. That means we are restricting the flow from inside to outside. Void domain will be outside this geometry, right? So let us identify regions. We can identify the fluid region using offset method, and in this case we have to define the location of this geometry inside this object. We're having different methods also, like excluding offset, we are having methods of centroid of the objects or numerical inputs also. Offset method is easiest one. Now For selecting the fluid domain, let us consider the inlet cap opening. So this is showing that inlet location, and to provide the fluid domain, we need to insert that diamond inside this geometry, and that can be done using offset of x value. Let us put the x value to be 50. That means that diamond has gone inside. Let us check it from clipping planes. You can see that diamond is inside. That means we have got inside location of this wind tunnel. Now we can define that fluid domain. Next to that, we have to create some kind of void domain to restrict the flow of fluid from inside to outside, and we should define that zone as void, and it can be done using any other method like centroid objects or numerical value or offset method, and we need to define that location of void domain. Diamond is showing inside location of this geometry. The location of the diamond should be moved away from this object. That can be done using offset method. Let us put y equal to 400. Okay, fine. That means the domain we are providing, which is away from the object. Let us identify the region. It is done. So two domains we have already created. One is fluid domain, another is void domain. Excluding that one, another solid domain has already been created by default. Next to that, we have to move on to leakage threshold. In our model, we are not having any kind of leakage, so we can skip to the next part by updating no leakage. You can see three domains have been identified. One is fluid domain, another is void domain, and by default solid domain has been created. The solid region is showing as void, that we identified as solid. We need to generate surface mesh with the best option of polyhexagon mesh. Void region doesn't require to be meshed. We need to mesh the fluid region and also the solid region. Let us update this surface mesh. Next to that, we need to select the default meshing control options. And we're generating surface mesh with a targeted skewness of 0.8, and from advanced options we're selecting separate contact pairs with a minimum global number of 1. Let us update the surface mesh. Surface mesh is generated. Next to that, I'm going to select updated boundaries. It has got defined walls and 2 pressure outlets and 1 velocity inlet. That to be updated. Let us update that boundaries. Let us decrease the numbers of boundary areas to 2 numbers, and let me add boundary areas of 2. Next to that, we need to generate volume mesh with the default setting, and we're keeping the quality improvement limit of 0.04. Let us generate the volume mesh. You can see the volume mesh is generated, and minimum quality is 0.2 and cell count is 88,275. Next to that, I'm going to switch on to solution mode. In solution mode, first of all, we need to select the units, and length we are considering as millimeter. Let us close it. Next to that, we have to select the models, and from here it will be considered as viscous laminar flow. Next to that, I'm going to select materials, and in this case material is not having any kind of importance, so default material will be considering, and default fluid also air will be considering that one only, and cell zone conditions also need not to be defined. The existing default materials will be considered as cell zones. Now I need to apply boundary conditions. As it is having one entry and two exits, so at the inlet location we have to apply velocity inlet or mass flow rate as the boundary conditions. Let us apply initial boundary conditions at the inlet location. Let us apply a velocity of 10 meter per second at the inlet location. Apply close. Then at the outlet location we have to apply 0 gauge pressure. Similarly at the exit 2 also we will be applying same gauge pressure of 0 value. Apply and close. Next to that, I'm going to select methods. It will be definitely simple methods. And for better discretization, let us select green gauss node based method, and it will be second order upwind. Next to that, I have to select initialization. Let us select hybrid initialization. It's done. Next to that, I'm going to select calculations, and I will be starting 100 numbers of iterations. Let us calculate. Iterations have already started. Calculation is complete. Next to that, I'm going to select results, and that can be viewed from here. And as you want to see velocity and pressure distribution at the exit openings, you can see results from here, and you need to see results from surface interiors. It will be facet average, and want to see pressure distribution at the exits. Definitely it will be 0 gauge pressure as provided by the boundary conditions. So we need to see velocity distribution here. At the exit openings, that is exit cap 1 and exit cap 2. Let us compute. You can see velocity distribution at downside it is 6.47 meter per second, and at the top side it is 8.28 meter per second, and net velocity is 7.37 meter per second. Initial velocity was 10 meter per second, right? Next to that, I'm going to show dynamics of flow particles through this wind tunnel that can be viewed from path lines. Let us select our new path lines, and I'm going to show particle variables throughout this wind tunnel. Let us show the dynamics of flow particles. You can view this one here. Now that can be seen in the form of an animation. Let us pulse it. You can see how the particles are moving from entry to exit, and it is being diverted at the baffle. After being diverted at the baffle, it is being circulated behind the baffle. Let us stop it and close it. We need to show different velocity profile and pressure profile through different planes. We'll create a plane surface. Along XY plane. Let us create. Now we need to see pressure distribution along this plane that can be viewed from contours, new contour, and we want to see pressure distribution through plane number 8. Let us save and display that pressure distribution. From here, you can see initially pressure at the inlet location is very high. It is indicated by this color, and at the exit location pressure is 0 as it is determined by the boundary conditions, and at the junction of the baffles the pressure is also very high. Let us say velocity distribution also. Through plane 8. Velocity distribution is also showing similar trend. At the entry location velocity is very high, and at the exit locations velocity is very less. Next to that, I'm going to select meshing. We select mesh with edges and nodes, and we want to select node mesh throughout the body. Let us display the mesh. This is the meshing conditions. Next to that, I'm going to select a scene which will be providing mesh together with some pressure distribution and velocity distribution. We'll select mesh and also the contour of pressure distribution. In this case, we can make the meshing as transparent one. Let us select mesh and also the dynamics of flow particles. You can see here the flow particles, how it is moving, and also the mesh conditions together. You can see at the baffles location some diversion is happening. at the location of baffles, some diversion is happening, right? With this one, we'll conclude our analysis. This is a very simple analysis of wind tunnel having two exits and one inlet. With this one, we can see that how the velocity is varying at different entries, and also the dynamics of flow particles we have seen at different locations. Thank you so much for watching this video. Thank you again. Bye.
If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.